Okay, so our next presentation is once again Dr. Sergio Ammirata. He's an active member of the Rist activity group within the Video Services Forum, as is Ciro. And he's with a company called SipRadius, also known as Ammux, and several other things. But one of the things that Sergio's been working on very diligently is a new authentication protocol for the latest version of the Rist specification. And he's here to tell us about that today, I think for the first time. So thank you very much, Sergio.
Good afternoon, I'm Sergio Ammirata. And let me start with a little preface to this talk. I and an associate, Heis Peskens, were the main contributors to a new authentication protocol. This protocol is based on some new secure existing protocols. It was added as an annex to the Rist protocol by the Video Services Forum, like was said. The Rist protocol, for those that are not familiar with it, it's a fairly new error correction protocol, and it's oriented for media streams, and now with the advanced profile for everything else, and of course with an eye towards interoperability. The authentication protocol, the new authentication protocol, is optimized for UDP applications. And UDP, of course, means that you sometimes have to deal with packet loss. With that in mind, we thought the new authentication protocol would be useful for other UDP applications as well, not only Rist, not only media streaming. So we've submitted an internet draft, which is a first step to an official IETF RFC. And in this talk, we will discuss some of the details of this protocol. Okay, so the protocol is called EAP SHA256-SRP6a. That's a bit of a mouthful. Of course, the name comes from the existing security protocol that it's based on. That would be the extensible authentication protocol, the secure hashing algorithms, and finally, the secure remote password protocol. What we're doing this presentation is to tell you a little bit about the specification and what it's for. We will get a bit technical, but we'll save the gory details for the last part, which we'll skip over really quick. Along the way, we'll hopefully make the back and forth process interesting enough so that non-programmers can get a good sense on how a security protocol works and what are the practical advantages that it offers. Okay. So first, let's talk about what's new, what's the new authentication protocol is for. Okay. So the Rist specification documents a couple of types of encryption for the stream it carries. We have PSK, we have the TLS. In fact, some of the big three US networks already use Rist and quite extensively to protect their streams. So you can imagine that they are highly interested in the security of the streams above and beyond the encryption of the data. So to that, we've added an authentication process specifically for the PSK used. Before even one encrypted byte flows through the system for the actual stream data, we're checking that both the sender and the receiver are exactly who they say they are. And we do it in a way that is resistant to man-in-the-middle attacks. And also, as we mentioned before about UDP, we do it in a way that won't hurt if there's a drop packet or two during this handshake that happens. After the authentication, Rist will take care of any resending any drop media packets along the way. Okay, so we will look at two implementations of the new spec. The first is simply to show you the command line options in LibRist, the open source library, since it already has the authentication protocol baked in. The second part of the presentation will show you the back and forth messaging of the protocol and look at the actual mechanics and the format of the actual packets of the authentication protocol. Okay, so let's start with the LibRist side. There are two parts of the authentication implementation in the LibRist library. The first part is a password hash utility. It gets built automatically when you download and build the library. And this utility, on the server side, you use it to create a repository for all your users and their passwords. It's designed to work like the Apache HT password utility. So if you ever use Apache Secure Basic Authentication, you should feel right at home using our utility as well. So the example here creates a blank file, then fill it with 3 hashes for the users Tom, Rick, and Harry. And if you look down on the bottom, you will see the actual hashes that it's creating for the users. We don't store the password. These are one-way hashes of those passphrases. Okay? So this is an example of the command line when you start the server utility. So once you have the user password file, you just include it as a parameter to the command line, as in the top example here. You'll see we put a yellow highlight in the parameter pointing to the password file on the particular server. Now, this method is particularly useful when you configure the server in listening mode. Basically, the server waits for connections, then checks for the authorized user before sending any part of the media stream. So each of the users in the password file can connect in, assuming they've specified the correct passphrase during the connection process. An equivalent command line for the receiver side to connect would just have a single username and password, the one that belongs to that particular user. Obviously, the receiver doesn't have a store of passwords. They just know their own password or passphrase and no one else's. So the connecting side has one, the server side has the entire store. So now let's look at the messaging between the prospective client and the authenticator, okay? Like I said, to not bore everybody to death, I'm going to start with an animation, informal animation of the protocol, okay? So don't be insulted if you think it's too simple. So this little cartoon animation will provide an overview of the authentication process. We'll look at the actual message structures and the technical part after this overview. This is just for you to have an idea. So let's start. The client on the left-hand side is going to start the process, and he just sends a very short code to say he wants to initiate the authentication protocol. Okay? So the server responds with a coded request, which essentially says, who are you? The client sends an identity packet. This is equivalent to responding with their name. In fact, it might even be a numeric representation of the client host name, for example. So the server first checks to see if, it's a valid user. The server, having received the client identity, confirms it on the list of eligible users, and then proceeds to challenge the client or the connecting, client with 3 numbers. So one of these numbers is a random one. The other one is generated based upon an encryption algorithm, and the third one is a modulo from the results of the algorithm. So basically, it's a preliminary test for the client. If it can duplicate the one-way hashing algorithm using those 3 numbers, it can go on to the next step. Okay? So the client does the computation and responds with the answer. Now, Douglas told us that the answer is 42. So we'll let that number represent the response. As with most things crypto, that actual result will be quite a few digits longer, but we need something to fill in the little messages there. Okay? So the server, it would seem, has read Douglas' answer and confirmed 42 is the right value, but he's not satisfied. He goes ahead and challenges him again. So in any case, the server does a similar computation to the one the client did before. In other words, both sides have to do the same thing so that the other each can prove to the other that they say they are. The only difference is that the server may have to do this for a large number of clients. All right. So we send the similar challenge, and now the client says, okay. The client responds with M1 key, and we'll look again at the calculations later, but the M1 is 5 lines of nested mathematical operations. They use secure hash algorithm functions, exponential multiplications, and bitwise operations. The important thing is that we don't expose all the necessary factors to duplicate the operations at any point. A secure key exchange operation has to be resistant to man-in-the-middle attacks. So having a successful message of, okay, so hold on. The server then confirms the calculations for the client's M1, and it responds with its own M2 key calculation. The client then confirms that, or if not, drops the conversation. And finally, there you go. Having a success message at the end of this exchange is optional, so it's the client can or may or may not respond. But for this cute little cartoon, key exchange, it's mandatory to exit with a smile. So that's the end of a layman terms explanation. Now that you're awake, I'm going to go into more of the details of what actually happens, right? So let's go through the real message exchange now. What's really happening? So let's start with message number 1, right? In the first message, the client requests that the server initiate an authentication process. It doesn't provide any other information at this stage. This message is only a request to start the communication. And here in the packet diagram, we see the code is simply data where it says the number 1. It says 1 for the request to start the process of authentication. Go to the next one. Second message, the server, the authenticator server requests the identity to the client. Basically, this can be a host name or a username, whatever was used for the password files. And if you read the specs, it will tell you how to fill the codes with data. It's the same format for the header. The payload is different. In this case, the code to request the username is what's used, which is number 2. Message number 3. The client now reveals its identity. This is a username that was put into the user password file or a host name, or whatever is decided, right? I didn't put the packet diagram because it's identical to the other 2. It's just the code and data that are different. The payload, you just, slightly different. Message number 4. The server verifies that the identity is received from the client and that identity is in its file or list of valid users. If not, the server can respond with fake values that will fail authentication, and this is to ensure that username enumeration is not possible, which is a common denial of service attack to try to grab the list of users by just randomly asking for users. So if it's there, though, the server challenges the client to present a valid key. As part of the challenge, the server gives the client several random and calculated values. The test or challenge is that if the client is genuine, it will know what to do with these values. A correct client will perform a calculation with those values and present the results in its response, which will be then the next message. The documentation tells you how to fill in the various codes and values here. I'm not going to go into detail of that. And notice that the data is depicted on the bottom. It's an open area. It's a little bit larger than previous diagrams. That's because some of the data, payload is actually large, pretty large numbers, okay? Message number 5. In response to the server challenge, the client presents an ephemeral public key, which has as factors the values in the challenge it received. We'll look at the precise calculation of those values later on in the presentation. For now, just know that the user identity and the key are presented separately. You'll note this diagram contains one variable length in one variable data field with variable length as a payload. Okay, message number 7. The server examines and verifies the client key that it received in the last message, and then the server presents its own key to the client for the client to verify it in the similar way with the same algorithm. In this way, the authentication process, like I said before, forces both sides to prove to the other that they are who they say they are. It's a two-way authentication process. Keep in mind that if any of these steps along the way fails, the authentication process is broken off, disconnected. In a lossy network, however, where packets may drop, the protocol allows for a resend or retransmission of a message when you don't get a response back from the other side, which makes the entire algorithm resistant to packet loss and usable over UDP connections. The format of this response packet is similar to the last packet diagram we just saw. Message number 7. Just as the server mathematically tests the client to ensure it's genuine, the client examines the server key, and with the key received in the last step, the client confirms it's genuine. There are only 2 steps left. Each side now has to send a calculate value to the other, and this is a part of the animation that says, I'll raise you 100, like, the final exchange, right? By doing so, they will have proven each other's challenge. And this will be the real test, and we'll look at the way it's calculated in the last part, and the math behind this. The values of this last challenge are called M1 from the client side and M2 from the server side. And you see a separate space at the bottom of the packet diagram for it. The size of this payload is 32 octets. Message number 8. It's only after the success of this 8th message, each side can trust each other, and the format of the message is exactly the same once they validate it. And the success message with message number 9 is optional. In the case of the Rist application, after this optional message is when the application can start sending the stream. Before that, it's not allowed to send any data whatsoever except data that has to do with authentication. But let's take a step back and look at it from above, right? We've added a highly secure authentication protocol as a door to unlock the rest of the stream. And that's even before we send a single byte of AES encrypted data or any other type of data on the protocol itself. The stream encryption passphrase is in addition to the user passphrase, meaning you have 2 layers of protection, the authentication and the shared key that encrypts the stream. Additionally, as an option, and we're going to see on the next slide, you can add a message that provides a way to exchange a secret or a shared key so that you don't have to have that ahead of time. In other words, you can have a complete end-to-end authentication and then key exchange mechanism using this protocol. And let me clarify this additional feature, okay? It's not just about authentication anymore. With this set of messages, it's a message that goes in direction. Basically, the client can request the transmission of a shared key, which goes into an encrypted payload, against with the already data that the algorithm has derived. This protocol basically can support key exchange for decryption and encryption of the subsequent data. Whether that's a key or an entire configuration blob, it doesn't matter what it is. The point is they can exchange now, before anything happens, some sort of encryption initiation byte stream for the next step. So whatever application that this guards, it doesn't have to be Rist anymore, with the authentication process can then leverage the authentication process to obtain key data for whatever comes next on the transmission. So additional considerations that we can mention for this. I think we covered most of these points on the previous slides, but I'll reiterate. The protocol provides for a wrong answer message in order to trigger the restart of the process. And it also recommends you break off the authentication process completely and don't answer in certain circumstances for security reasons. And we already mentioned that this protocol is especially resilient for use in UDP transport. And that's because it allows for repeats of a message when no response has occurred from the other side, maybe because of a packet loss. One thing that we haven't mentioned, and it's important to say, is that provisions are made on the protocol for multicast UDP streams and for multi-link routings. Multicast, of course, is often used for media streams. And since this protocol works, or is a GRE and VPN friendly, we may have a situation in which multicast destination lies across a lossy network, or maybe your switch, has loss, or your network has loss. So also in transporting media stream, two service providers path support either redundancy or additional speed, and the protocol takes multi-link into account. So it's already designed to work on all those scenarios. Libris in particular already supports both multicast and multi-link using this protocol. Okay, in this final section, we'll show you some of the calculations, but to not bore everybody to death, I will just glance at the slides really, really fast. And anybody that wants to actually get the details, we have the link to the RFC. You can read it in its entirety. All right. First, we talk about the salt and the calculation, the key rotation. We mentioned some more things about the way the salt is used. Little salt, cute salt animation there or icon there. Then we give you some examples of how to do a challenge response for step 1, 2, and 3, and we specify. Not as detailed, but you'll see the details in a second. An example 2 from the other side. And then here's the really neat and gritty math around that M1 and M2 calculation. These are all standard algorithms that were glued together in a way to keep it secure and to make these things work properly. So to conclude, you can take advantage of the authentication protocol today for Rist, at least using the Libris library. You can read the internet draft and use it in any other applications. And hopefully you have an idea on how secure it is, what is it for, and we have not bored you with all the math. Thank you.
Okay, do we have any questions?
Sergio, have you submitted the internet draft yet?
It's being submitted this week. We had to reformat everything in XML to get it into this proper format. But the internet draft is ready. It can be viewed by anybody, and we'll finalize it this week for the first submittal.
Okay. Any other questions? I did notice on slide 17 you had an unmatched parenthesis. No, sorry, just kidding. All right. Well, thank you very much, and appreciate your time.